Alright, well, welcome to Oceanic Gyres, Boats and Debris. So I'm going to go over oceans a little bit, and then currents, and how debris gets out there, and why it's getting concentrated, where it's getting concentrated. Sort of whatever I can offer to help with your project, and then I'll give you my contact information so you can ask me any questions you might have. So a little recap on oceans, just in case 101 was a while ago or you haven't taken it yet. There's an uneven distribution between the land and the sea in the northern and southern hemispheres. In the north, 61% of the surface is covered by the ocean, and in the south, it's actually 81%. So there is a discrepancy, basically, in the amount of ocean versus the amount of debris. But it kind of makes sense. If you think about it, there's less ocean in the north, but there's more land. And if there's more land, there's more coastline. And if there's more coastline, we have more points of entry, basically, for debris to enter that water system. In the south, I have less coastline, I have more ocean. That doesn't mean, though, that I'm going to get fewer debris put into the oceanic system. It means I'm probably going to have more debris put in by shipping vessels, fishing areas, anything like that. So not really a shoreline-derived debris, but more of an ocean-going vessel-type debris. So we have a discrepancy in the size and the distribution of the oceans. We're also going to have this difference in the type of debris that you're going to see per ocean. Kind of highlight the difference that we're going to see here, and also the scale of it. When you look at the continents versus the oceans, there's an average continental elevation of just under 3,000 feet above sea level. Compare that to the average oceanic depth of just over 12,000 feet below sea level, and you can see that there's a significant amount of ocean compared to land. So this is not a small scale problem. When you look at the size just between the two, there's a lot less continent than there is ocean. So this problem is going to extend over a very, very vast amount of water, not only laterally, but also vertically. To kind of put that into more comparison for you, if you take the Earth and turn it into a marble, basically, it's going to be covered by one single ocean that's got an average depth of about 6,336 feet. So this is a very, very large ecosystem that you're seeing in the ocean, and that means that the problem you're solving extends over a very large area. Now, some teams have been talking to me about using a chemical method and monitoring basically particulate matter, which you could do, but I need to mention salinities if you're going to be thinking about any type of system like that. The salinity of the ocean is actually key to oceanic health and the ecosystem. We have very high salinities that are found in the dry subtropics. We have low salinities that you find in the mid-latitudes and near the equator. The poles are kind of all over the place due to sea ice. If you create sea ice, you raise the salinity, and if you melt sea ice, you lower the salinity, because basically you're adding or removing fresh water from the system. You can't actually entrain salt in sea ice, so it only removes fresh water. That means if you're just monitoring the particulate matter or the density of, let's say, concentrated materials in the water, you're going to see a spike as you get toward the poles anytime that there's sea ice forming. So you need to be really careful with this, because we want the sea ice there. This is a key part of the system. We really don't want to affect it. But at the same time, you do want to be able to monitor pollutants or chemicals entering the system. Just don't affect the salinity in the area. And so I give you the range there. Of the highest, salinities are going to exceed 4.2%, and the lowest can drop below 1%. So if you're going to design some type of system like that, you might want to keep that in mind and realize that there is a variability that we see in the salinities, and we just don't want to affect it because it will affect the ecosystem in a negative manner. So here are the oceanic currents. This is actually a basic map. It actually is a lot crazier looking than this when you look at a full map. The warm currents are in the red, the cool currents are in blue. And so you can see how water flows around the globe. The way this works is you have warm waters at the surface, and they are pushed along by wind and by the rotation of the earth. That's what gets the water mass moving, and then once it starts moving, the warm waters will move where they start to cool down. Cool masses sink, so it pulls that water mass toward the base of the oceanic floor, pulls it along the bottom, where it picks up essential nutrients and becomes enriched in these nutrients. And then as it approaches the equator, it actually starts to warm up and gets forced back to the surface, bringing these enriched waters up where they can be accessed by more animals. And this is a very, very important system. This not only provides a nutrients exchange, it actually balances out the temperatures of the globe. So this is the thermohaline circulation. And it moves garbage, unfortunately, as well. So what we're seeing is the garbage or debris, or even boats, are getting pulled along and kind of pulled off the coast by those cooler currents as they come up. And then they're pulled out into the open waters where they are traveling in the warmer currents, and then they kind of stagnate or get stuck when those warmer currents start to sink, or worse, some of those chemicals actually sink with that current, and we can now find them along the oceanic floor. This also affects animals because if you think about it, the animals know where those cold enriched currents are coming to the surface, like along here and along here. These are prime feeding grounds. So you have animals coming up and joining there. They're feeding on the nutrients that are coming out of those currents, and they try to follow them as far as possible. So when they get out in here where you're starting to lose a nutrient load in the water, but you still have all the garbage, there's not much left. And that's when they start really ingesting debris, especially the chemical kind, which is most unfortunate. So it's kind of a pervasive problem. Not only is it getting pulled off the coast here and you're kind of adding to the circulation here, you're also pulling chemicals in and putting them out in areas where it's not as nutrient rich and animals are looking for food, and it's almost like it's being offered to them. Now when you look at this, you can see that the currents are kind of circling certain points of the globe. These make the gyres. So this is a simplified map of those gyres: North Pacific, South Pacific, North Atlantic, South Atlantic, and Indian. What you can see is all of them are driven by the same mechanism. You have some cold current coming up to surface. It pulls along a coastline, heats up, circles around, then that mass is going to cool back down and sink. In this case, it's joining with polar waters that force it to sink. Okay, so you have these gyres that are going, and they're very large, complex systems. They're not like a whirlpool. They're much, much bigger. They're not sucking things down to the bottom. It's large, slow movements of very, very large masses of water. So here's another map of this, and it shows that they're actually a bit more complex than we kind of visualize. For example, here we have the North Atlantic gyre. So things are coming off along, they're circling down. They actually go through the Gulf of Mexico. They pick up all sorts of goodies in there. Come back out, come over here. This warm current, the North Atlantic current, can actually join the Norwegian current up here, and that's its own gyre, locked up here near the pole. Okay, so it all feeds together. So it doesn't matter where a pollutant or a debris enters the system. You can pretty much get it anywhere on the globe after that. Once it's in the water, it's going to freely travel. To kind of highlight this a bit more, here it's just the Pacific. Here's the South Pacific, North Pacific, and then the subpolar gyre. And these are all pulling material off coasts and kind of entraining them in these oceanic masses. So you can see here, things are pulling down. This is the California current, but it actually starts up near Washington. Pulls it down, comes along, goes over here. Okay, so it actually pulls through most of Southeast Asia, East Asia, Japan. Okay, we've got pieces that circle this way and pieces that circle back this way, south and north. So it comes up, comes in, comes around through here. We've got pieces in that break off and get locked up here in Alaska and circle out through their own way. So we have all these different water masses contributing to the problem of oceanic debris and pollutants in the water. Each of these gyres have a different type of pollutant in them. So this subpolar gyre, for example, is pretty famous for derelict boats, fishing remains, nets, etc. There's a pretty good fishing industry in the Bering Strait, right? So anytime a boat goes down or people just cut the net, it gets entrained in the subpolar gyre, which might donate it then to the North Pacific gyre, which has pieces getting pulled along here, like from Hawaii. And there we see a lot of scuba gear, tourist-based materials, flip-flops, lots of flip-flops, okay? And those are going to join the fishing boats. So this is more of a fishing-based thing. This is more actually tourist and coastal trash-based. And they're all meeting together, and then it circles out this way, and it might actually make its way down through here into the South Pacific gyre, which honestly sees more kind of fragmented remains of boats, some trash from the shoreline, mostly in that case packing material, and you'll see why in just a minute. But they each have their own type of trash. So if you're thinking about specializing, you really need to think about what each gyre is going to have. For example, if I'm going to design something to take out boats and remove them from the water, or the fishing nets even, that's not going to be as relevant down here in the South Pacific as it would be up in the subpolar. This is where the boats and the nets are. That's their source. It's not so much down here. That's more like styrofoam, building debris, okay, wood. That's kind of more what I see there. So you're going to want to think about what are you specializing in removing if you're going to go that route. How material gets from the shore into the oceanic mass is actually due to tidal currents, okay, or just plain tides. These are part of the oceanic system. They're very important. This is a vertical motion of the water near shore that's going to cause the water level to shift horizontally, and that creates a current. Either it pushes toward the shore or it pulls away from the shore. So when it pushes toward the shore, you have water level that rise, and this is a flood tide. When it pulls away, the water levels drop, and this is called an ebb tide. This is important because of what it does with the trash, and you can see that in this pretty cool little graphic from NOAA. What you want to keep your eye on is that really nice piece of floating seaweed. That's kind of modeling what debris would do. At high tide, the water comes up pretty far onto shore, and it kind of depends on where you are in the world for how high it's going to go. But in this case, it's coming up pretty high. So if I have any debris or trash or anything, really, if I was kind of lazy with my fishing nets one day and left them here, when that high tide comes up, it's going to grab them, just like that seaweed comes to shore. Now in the ebb, it's going to pull it offshore and pull it away from where we might be able to retrieve it easily. So you can see that piece of seaweed gets pulled further out into the basin. That's when it gets added to the oceanic current, and that's how it starts to enter those large gyres. So just because something's on the shore doesn't mean that it can't somehow end up in the middle of, say, the Pacific. All you need is one good tide that can pull it down and in, and then the system actually kind of pulls it out into the basin automatically, and puts it into that water mass. Here are the shipping lanes worldwide, because I'm not just getting things from shore, there's also things coming off of boats. So you can see that it's pretty heavy in terms of shipping between different continents, crisscrossing the oceans. You can also see why this might dictate what you see in a gyre. For example, when I said that I don't really see that many derelict boats, etc., down in the South Pacific, honestly, it's not that heavily populated in terms of shipping lanes when you compare it to, say, the North Atlantic. So the type of debris I'm going to see, the amount of debris getting added, you kind of have to pay attention to your shipping lanes too. They're responsible for a significant amount of material that ends up in the water, either intentionally or unintentionally, as you'll see in a moment. So you want to kind of think about where the gyre is located, and if you're thinking of hooking something up to one of the large cargo ships, you might want to make sure something actually goes through the area you want to clean. If I'm going to design something that attaches to a freighter, and I want it cleaning the South Pacific gyre, it's really not going to be terribly effective. There are shipping lanes, they are in use, they're just not as heavily used as other lanes. So for something like the North Atlantic gyre, I could get away with that as a more effective method because I have a lot more boats in that area that are crisscrossing there a lot more frequently than they are other places of the world. Here's another little graphic to highlight that. This is just the commercial shipping lanes. Here's Anchorage, here's Victoria, Seattle, Vancouver. So you can see there's really heavily traveled lanes coming in and out of different ports. And then there's some zones where we really don't go very often for various reasons. Could be currents, could be boating hazards, whatever it is, we just don't use it as often. So that might be something else you need to keep in mind if you're using something off of one of the commercial ships. They don't go everywhere. They have very strict lanes that they're allowed to use, and that might be something you need to keep in mind. These lanes also, just because they're really dark doesn't mean, oh, this is the most popular. It also tells you about the population. Yeah, it's really heavily used, but at any given time, there's a lot of boats on it. So that's also something to keep in mind. Not only is it a very popular route, I have a lot of boats on it. So if I'm going to drag something behind one of those commercial vessels, A, I have to make sure I'm allowed to drag something behind the vessel, but I have a lot of boats in that lane. So I could potentially clean something rather quickly if I could figure out how to leave all the fish behind and relatively untraumatized. Here's a map that shows your zones of most pollution. This is a map from 2002, so this is actual data. This is from 2050, so this is projected data. As you can see from the map at the top, it's not looking so good already. We do have zones that are still green, which means low to no noted pollution. Okay, and this is measured on the beach and just offshore. And by just offshore, we mean waters that don't exceed 60 feet. Okay, so I can't go more than 60 feet depth on this particular map. Unfortunately, most of the coastlines, as you can see, are red or yellow. There's even zones of brown. And over here too. Brown equals high to very high pollution input, either on the beach or within 60 feet of water. So we have some of that near some of the larger populations, and we have a fair amount of that medium to medium high pollution right on the shore coming off of it. Now by 2050 we project almost all shorelines will be brown, with very high amounts of pollution either on the shore or coming off it. Now there were some comments and questions before I made this, asking about, well, how do things get in there? I mean, not everything's intentional. People don't just go by and throw things in the ocean. No, it's not intentional. Sometimes it's accidents like this. This is a cargo vessel that didn't make the turn quite as well as they thought they were going to. This is not very deep water. In fact, the bottom of the ship is actually touching base. It's not good. It shouldn't do that. But as you can see, the cargo has already tipped off the ship. There used to be containers all through here stacked that high. So if you tip that back up and put all those back, you can see that they've lost a considerable amount of their cargo. And these either sink, or they break apart, or they float away. Kind of depends on what's in them. So we have what we call flotsam and jetsam. So flotsam is material that is basically non-intentional. We don't mean for it to get into the ocean. It floats off the shore, it floats away from a wreck, it accidentally falls overboard and we're not able to retrieve it. It is the wreck. Basically, it's material we didn't mean to get into the ocean. Then we have jetsam, which is material that is intentionally jettisoned. So if these guys had been intentionally knocking their cargo off the ship, that would be one thing. But they're not. So we do have this accidental input of material. We also have the non-accidental input of material, or the jettisoned material, which ends up anywhere in the oceanic column. You'll have people throwing trash overboard these large vessels right out in the middle of the ocean, so it goes straight into the gyre. So that's something else you need to consider. The point source of the trash is not just the shoreline. It can actually enter the system anywhere in the entire circuit. To highlight this, behind those people is, in fact, a very, very large pile of trash. That is material that was sifted out of the ocean after the Japan tsunami in 2014. That is all accidental. Obviously, no one wanted any of that to happen, and no one wanted any of that to end up in the water. All we were able to do, though, is drag it to shore, or watch it wash up on shore in other places. So now it's just sitting there, in most cases, and slowly re-entering the system. But to kind of highlight the vastness of this, I mean, these are people. That is a very, very large pile of trash, and that extends for a significant distance. So you can see that it has a very high potential to re-enter the system. This is right on the beach. And once it does, that's a lot of material that could slowly sift back into the ocean. This is a pollutant map to show you the concentrations of pollution of various sizes. So this is 0.33 to 1 millimeter diameter pollutants. As you can see, exceedingly large concentrations. Okay, and those are the gyres, so they're right in it. This is 1 millimeter, just over 1 millimeter, to 4.75 millimeters. You can still see it's sitting in those gyres. Okay, let's go even bigger. This is 4.76 to 200 millimeters diameter. Well, pretty much only have big concentrations now, kind of at the heart of those gyres. Okay, and even down here, it's not really all that concentrated. Greater than 200 millimeters, so things like boats. We got a little bit out here, but otherwise we don't really have that big of particles. So that should tell you the size of the particle you're actually dealing with in terms of concentration. Far more popular at these smaller sizes than at these much larger sizes, which are easier to retrieve. Here's a relative debris density per unit area. And you can see that we can see the gyres, part of them anyway, and some spots that aren't even gyres. Those are just heavily polluted shorelines. What it works out to, though, is you're looking at 3 or 4 particles of material per square meter in the really dense zones. So when you think about like trash islands or these huge systems of all this floating trash, what comes to mind is trash packed all together. Oops, my picture of trash disappeared. Anyway, what you see is all this trash packed together in your head, but that's not what happens. It's these particles that are fairly diffuse and they're fairly small. And by particle, we do mean anything from 0.33 all the way up to greater than 200 millimeters. So a particle is relatively undefined, but we do know that If you do the math, it's about 3 to 4 per square meter. It's not huge. There's just a lot of them. And if you think about the square meters of just, say, the gyre, then you start to see the problem of how much debris is actually out there. So, unfortunately, my trash picture disappeared, but if you have any questions, this is my email. I'm more than happy to answer any questions you have about it. Or if you want to stop by and chat oceanic systems, how trash is getting in the ocean, how long it stays out there, things like that. I do have an office in the Green Center, 265. It's a classroom, but on Tuesdays and Thursdays from 10:50 to 12:15, it's an office, and I'm in there. So I would be more than happy to answer any questions you might have. Thank you.